Three, two, one. All right, here we go. Our first pre-recorded video. Pretty exciting. All right, and what are we going to talk about? Well, our goal, again, remember, is to fix the Riemann integral, so we should probably actually talk about the Riemann integral and the nitty-gritty of all of it, and kind of hopefully start seeing what's exactly theoretically wrong with it, and then work towards fixing it. All right, so from calculus, recall that the Riemann integral is this following collection of symbols, right where we take our interval AB, we've got our function on it, we cut the interval up into sub-intervals, measure the width of all of those, which is pretty easy to do for a sub-interval. It's just the difference of the right-hand point with the left-hand point. It gives me my widths here. We pick points in between. Now, sometimes you'll pick the left endpoint, the right endpoint, the midpoint. There's all sorts of choices that can be made, but generally speaking, just pick any point. And then you can make this, which is the area of a rectangle. And then the idea is you add it up, and then we'll take the limit as the biggest subinterval, and this is usually referred to as the mesh of the partition. We'll take the limit as this thing goes to 0. Now note, this limit is a little suspect, because while this is a real number approaching 0, the thing inside of these double bars is actually a subset of real numbers. So that note is different than how limits so far have been sort of discussed. So we really got to make this a bit more rigorous, right? In calculus, you can just wave your hand pretty good here and go like, oh yeah, it's a limit, no, don't worry about it. Right, because very quickly we just point out that, oh, this is connected to antiderivatives, and then you just turn this into computing antiderivatives. Don't even bother with this limit definition. All right, but, right, for us that's not good enough. We need a nice rigorous epsilon delta argument, so we've got to go through and piece all that together, which will be the goal. All right, so let's note that kind of the key thing here when it comes to integrals is this notion of partition, so we want to make that nice and formal, so we'll start there. So a subset is a partition of an interval if it's a finite set and it has the endpoints. That pretty much does it, right? So note, because it's finite, that means it's a list, and because we have the two endpoints for sure, the list, I'll start counting at 0. I know, disgusting, but as is tradition. But fortunately, the end does come out of the natural numbers, which start at 1. So, because the left endpoint and the right endpoint are generally distinct entities here. And note that, right, it's a finite set, so there's a finite list, and the x0 and the xn are the two endpoints. All right, and no, that's it. That's all a partition is, no more nor less, and we'll always have the opinion that we've put them in strictly increasing order, which you can do. So if you want a fun proof to work out the details of, given a finite set, show that you can arrange it in strictly increasing order. You prove your favorite sorting algorithm actually works. Cool. All right, now obviously, with a partition in hand, then we can easily define the delta x's, which are just the right endpoint minus the left endpoint. Note these are always positive quantities. And furthermore, something we will frequently use is that if you add all of these up, you just get the length of the original interval AB. That's pretty easy to see because the sum of these will be a telescoping situation, and as we've pointed out, telescoping sums will, right, maybe, did you hear that beep? I don't, anyway, that was my computer making noise. I don't know if it picked it up. Now it's just me, rambling to myself. Okay, anyway, so when you add them all up, you get the length of the interval. That's something we'll frequently exploit. All right, great, so partitions are down. Now what are we going to do? All right, well, if we looked at the setup here, I got the partitions. Well, now I'll, pick points and do this multiplication, right? We will, but not right now. We're going to save that one for later because it turns out that while these traditional Riemann sums can be made very rigorous, we can actually make our lives a lot easier if, instead of picking points and making these rectangles, we look at, of course, our favorite tool in analysis, which are supremums and infimums. All right. So if I have a function and it's got a lower and upper bound, then for each partition and any subinterval, the function's bounded on the subinterval. So that means that there's a lower bound for my function and an upper bound, which means I have access to a inf and a sup. So this set is not empty and bounded. And hey, we'll give symbols for those, and here's where the notation starts getting great. So here I'll do little m of the partition P, k for the kth subinterval, and my function f. So the little m is for the infimum of my function. We're on the kth subinterval of my partition P. Okay, and similarly we can get the sup. Now, note, the inf and the sup are going to bound any choice of a output for f, so this gives me kind of an extreme case of a lower and an upper of, hey, if you pick any point in the subinterval and look at f of ck, well, the f of ck is always bounded below by this and bounded above by that, so that kind of gives me extreme things to work with. Right, and if I'm looking to take a limit of that, if I have a lower and an upper and I can make them collapse onto each other, hey, that'll make life great. All right, so the unfortunate thing is that this notation is going to be flying around a lot, and it takes like a second to get used to. So this is a good pause the video moment and really digest what's going on here. All right. And note, furthermore, that these things are bounded above and below themselves by whatever upper and lower bound you have for your functions. So that's occasional thing that we'll do. So sometimes you'll make these like really extreme estimates on your function, and those can actually help you. Right, cool. Okay, now that we have all of that in hand, now what we'll create, similar to the traditional Riemann sum, where you take your function evaluated at a point and multiply it by those delta x's, I'll multiply those delta x's by these infimums instead, and that'll give me what's called the lower Darboux sum. Now note, it's not the traditional Riemann sum. This is not your function evaluated at a point. It's rather the infimum of the function on that subinterval. And similarly, the upper one gives me that. And again, if I want to make a limit of things, having an upper and a lower that I can collapse onto each other. All right, we've been pulling that move off, so it seems like a good idea. All right, great. So, equipped with those, let's actually start proving some things about these upper and lower Darboux sums. And again, note the notation. The lower Darboux sum of the function f on the partition P is a typical Riemann sum, only instead of evaluating the function at a point, I'm computing its infimums on all of the subintervals. Okay. And let's note that we have the following. That's pretty easy to see, that any upper bound of my function is going to give me an upper bound on any of these upper Darboux sums, and any upper Darboux sum is obviously bigger than any lower Darboux sum. So Darboux, by the way, mathematician, great. I don't think I pointed this out when we talked about the intermediate value theorem. So continuous functions have the intermediate value property, and a natural question was, if you have the intermediate value property, must be continuous. Darboux is the one who ruined that idea by cooking up a way of demonstrating that, well, actually, you can have the intermediate value property but not be continuous. Anyway, cool stuff on Mr. Darboux, but he also had this idea of not streamlining, but a different approach to Riemann's sums, where instead of using the outputs of the function, we'll use their infs and sups. All right, and yeah, so note every lower Darboux sum is less than every upper Darboux sum, and those are bounded above and below by whatever the upper and lower bounds are from our function, multiplied by the length of the interval. All right, and quick proof of this. So take your partition. By our hypothesis, we know that the lower, the inf and the sup of the functions on the subintervals are bounded by the alpha and the beta. We know that the sum of all the deltas is b minus a, so then it's just follow your nose on that. Right, we know this will add up to that, okay, and we know these are less than those, and hey, there you go, there is our lower Darboux sum, there is our upper Darboux sum, and that's proven. Alright, pretty cool. Alright, so there's our first little taste of working with these things, and again, I will stress this is notation overload, and buckle up, buckaroo, it's only going to get worse. Alright. So let's go ahead and prove what is the defining fact here. This proposition right here lets us get away with everything that we're about to do, and that's the following statement. If I have two partitions, one of them is contained in the other, so note this partition will have less points than this partition. They're both finite sets. And what happens if we add more points to our partition, so you have more subintervals, you're refining the sum? Well, what we would like to happen is that the lower Darboux sums get bigger, and the upper Darboux sums get smaller. And that would make sense if we're thinking about how Riemann sums typically work. When you make smaller and smaller subintervals, your approximation gets better and better. And so again, the Darboux approach here is to have these upper and lower bounds and refine it so the uppers are going down and the lowers are going up, and they hopefully get arbitrarily close and meet somewhere at some point. Okay, so this ends up being the linchpin result. Once you have this, then pretty much everything is for free. And how does this one work? Well, this one we can kind of reduce down to a few things. So first of all, I'll prove the first inequality, and then just note the second inequality is the same thing as the first, but with soups instead of nths. And moreover, we really only need to figure out what happens when I add 1 point. Because once you see why it works for 1 point, then you know why it works if you added 2 extra points, or 3 or 4 or 5. And again, remember, these are all finite sets, so I'm only ever adding finitely many. So once I see how it works for 1, dunzo, I know how it works all the time. Alright, so what happens then? Well, if we let P be our traditional partition from x0 to xn, then the partition for R is going to be a list, and we'll call those y0 to yn plus 1. And note the only difference is that somewhere in there we've added the point y. So when I'm looking at the lower Darboux sum of P, and I want to compare it to the lower Darboux sum of R, I basically just need to split it into 3 parts. So what's happening before we get to the added point, what happens when the added point shows up, and then what happens afterwards. Okay. So, first things to note, before we get to the added point, then, well, all of the subintervals are the same, nothing has changed, and so that means all of the delta x's and delta y's are the same, so the infimums are all the same, and so everything's just the same. So, all of these ingredients to the lower Darboux sum for the partition P and the partition R, well, they're all equal to each other, so when I add them all up, they'll all be equal, so nothing happens. Alright. Alright, now what happens when we get to the extra point, right? Once we get to J, that's where Y is going to appear. Okay, so let's break down what happens there. So if I look at the J subinterval for Y, okay, well, this is still x sub J minus 1, but Y landed between x sub J minus 1 and x sub J. So this interval is contained in that interval, which means that the infimum on this set is no more than the infimum on this one, right? This, right, we added more points, so the infimum can't get any smaller, right? If you start removing things, the infimum can only go up. So the lower, the infimum on the J subinterval cannot exceed the infimum on the J subinterval for R, because there, right, we've added in more points, so because of that, the infimum could only get smaller here. It can't get bigger. Right. All right, and similarly, if I now go up to the J plus 1 subinterval for Y, that is also contained in the J subinterval for the partition P, and so here we see at the J moment, the J the J subinterval for P, the infimums there are all bounded above by these two, so they're bounded above by their sum. And if we multiply in the width here, right, well, that width we can sneak in the y, and each part here is less than the individual ones. And there we go, at the J moment in the Darboux sum, this part is less than these two. So now when I look at the J plus 1 subinterval for x, well, now everything just lines up. because now we've skipped over the point y, and at that point everything lines up again, and so then all of the sums will work out, and then our punchline works out, because the only thing I really need to worry about is when that point y shows up in the partition. And there we see basically you split the interval, and the partition on for P, the k spot for it, right, will get bounded above by both the k and the k plus 1 spot for the partition R, and there you go, proof's done, we got it. Right, pretty straightforward, right? There you go. So now we know that when you refine a partition, when you add more points, the lower Darboux sums get bigger, the upper Darboux sums get smaller, so we want them to collapse in on each other. And note, what does this mean now? I just proved that this set, the collection of lower Darboux sums, is in fact bounded above. Right, is bounded above by any upper Darboux sum. And similarly, the collection of upper Darboux sums is bounded below. Right, they're bounded below by any lower Darboux sum. So this has a sup, this has an inf. So we're pulling that sup of inf and inf of sup maneuver again. And indeed, we'll define the lower Darboux integral to be the sup here of all of the lower sums, and the upper Darboux integral to be the inf of all of the upper. All right. And now, obviously, I'm going to want these things to line up with each other, and that'll give us the traditional Riemann integral. And note, we built our way there using sups and infs. Pretty cool. All right, great. Okay, so there we go. We've made kind of our first step here to get a nice, rigorous epsilon way of arguing about how integrals should work. And we're using the building blocks of the real numbers, sups and infs, to make them work. All right. So let's actually prove, note that we didn't explicitly do this yet, but let's actually prove that the lower Darboux sum does not exceed the upper. So take a partition. For any partition R, it follows that when I union these two together, I'm going to get a partition that's bigger than both of them. So that means if I look at the lower Darboux sum, I don't know if you hear the cat yelling, but it is, on P, that is less than the lower Darboux sum on R union with P, which is less than, of course, any upper Darboux sum. And as we pointed out, if you refine a upper Darboux sum, you will get smaller, so we know what that one is less than that. And note P and R here are arbitrary, any two of them, it works, so that means any lower Darboux sum is a lower bound for the set of upper, and thus we'll get this, which means then that the upper Darboux integral is an upper bound for the set of lower Darboux sums, and so it can't exceed the sup. It can't get smaller than the sup, I mean, the other direction. And there we go, we've got the inequality. So naturally, then, Riemann integrability we will count as when those two things line up with each other, but it's possible that they don't. And we already know they don't, because we already know a function that fails to be Riemann integrable, but now we'll get an explicit, here's why this one falls apart. So again, we look at our good friend the Dirichlet function, which is 1 on the rationals and 0 elsewhere. Any partition, the infimums will all be 0, because you can always find a rational number in between any two real numbers, and similarly the sups will always be 1, because you can always find an irrational number between any two real numbers. Alright, so the lower ones always add up to 0, the upper ones always add up to 1, so the lower Darboux integral is 0, and the upper Darboux integral is 1. So note, this actually gives you a way of, similarly, when a sequence fails to converge, well, it will still have a lim inf and a lim sup, and hey, here we see that kind of idea is reflected with these Darboux integrals. Pretty neat. Alright, and so then naturally, the Riemann integral can be formed by going, well, if these upper and lowers line up with each other, we'll call you Riemann integrable in that case. Alright. Okay, and for keeping track, and rather than just writing the word Riemann integrable constantly, we'll use the symbol RAB to mean we're dealing with Riemann integrable things, and because these two quantities coincide with each other, we can just give it one symbol, and it's the traditional integral from A to B. Cool. Alright, so let's make our first epsilon attack here for the Riemann integral. So here we'll see that a function is a Riemann integrable if and only if, given an epsilon, there is a partition so that things are working, and in particular, that means that the upper and lower Darboux sums are within epsilon of each other. All right, cool. So here's our first attempt at an epsilon. We'll go ahead and prove that.